Hey, college algebra kids. We're going to pick up with parabolas here. We're going to put a little extra onto the end of this video. I'm going to show you something that makes math kind of cool, something I've just been thinking about. But first, let's get to vertex form. We know that standard form is y is equal to ax squared plus bx plus c. And what we have with that is, we have our a, b, and c values, but the vertex form is y equals a times x minus h quantity squared plus k. And you can see from what we've learned so far is that this guy in here creates the horizontal shift. This thing on the outside there creates the vertical shift. And then this a value is the flip or the stretch or whatever it might be. But you can see that because of these shifts, you end up with hk being your vertex. And so what we want to do is we want to take this function, and I'm going to write as y is equal to x squared minus 6x plus 1. I'm going to write as y equals. And as I place this into vertex form, what we're going to do is we are going to complete the square. So I'm just going to drop some parentheses there. Put the 1 on the outside. And in order to complete the square, we take that 6, we divide it by 2 to get 3, and we square it to get 9. Now, this is where I'm going to defer from what we did earlier in the class. Notice if I add the 9 there, I could add the 9 over on this side as well. Well, eventually, when I solve for y, I'll just subtract 9 from both sides. So the whole point of this is to get you to understand that instead of adding 9 to both sides, that maintains equality, obviously. Adding the same thing to both sides maintains equality. But you can also do this. You can add 9 and subtract 9 from the same side. That maintains equality. The net change is 0. So we get y is equal to x minus 3 quantity squared minus 8. And so therefore the vertex is 3, negative 8. You'd be able to graph it at this point over 3, 2, 3, down 1, 2, 3, 4, 5, 6, 7, 8. You can see if you needed to know the axis of symmetry, it's just x is equal to 3, that vertical line that goes through. Looking at this graph, you could also see that the y-intercept is 1. You can just, plot that 1, flip the value over here to get another spot. And you could draw a pretty quick graph, no big deal. And sometimes you just want to be able to determine if there's a minimum or a maximum. And so we're not going to go into a long description about minimums or maximums, but you can see in this situation, because the graph goes up, there's a minimum. And the minimum value in this situation is negative 8. So not really that important when it comes to parabolas and its understanding, but something that comes up sometimes on ACT questions. Does this function have a minimum or a maximum? And you can tell there. So here's that sheet of notes I gave to you. But let's do 2 more of these. This one's a little bit different. We have y is equal to a negative x squared plus 4x. I'm going to write it like that. And what I'm going to do is I'm going to factor out the negative. This is where we have to be careful, okay? So I take the 4 and divide by 2 to get 2, and I square it to get plus 4. Now, from what I just said, you would then subtract 4 on this side, but that doesn't work. And here's why. This 4 that you have sitting right here, it's not actually a positive 4. It has a value of negative 4. You've actually subtracted 4 from both sides. You have to consider this negative sitting out front there. So therefore, in order to maintain equality in this situation, or a net change of 0, we would then subtract 4. I'm sorry, add 4. Okay? And if you don't believe me, at any point you should be able to combine like terms and come up with what you have in the beginning. So I'm going to do that and erase that. Watch what happens if I go a negative x squared here, I go plus 4x, and then I've got a minus 4 and I got a plus 4. Notice those cancel. I get 4x minus x squared. Okay, that's what I started with. So I know I've maintained equality the whole way through. So I know that this is correct. I just factor this down. I get a negative x minus 2 quantity squared plus 4. And so the vertex is 2, 4. The direction is down. I go over 2, go up 4. If you look at the original equation, you can tell that there's no c value, so the y-intercept is 0. The axis of symmetry would be x is equal to 2. It heads down, and that's my shape. Has a max value of 4, if you're asked to list that. Yeah, so let's do one that's just a little bit more complicated. Hopefully you've got the general idea now. So now we have y is equal to 2 x squared minus 3x, and we'll put the minus 1 over there. As you've already guessed, we are going to factor out that 2. So I get x squared minus 3 halves x, and then a minus 1. So what we want to figure out is what number to add there to complete the square. In order to figure out that number, I take 3 halves and I divide it by 2, or multiply by 1 half, and I get 3/4. Excuse me. Now I square the 3/4, and when I square 3/4, I get 9/16. So you would generally want to subtract 9/16 from that same side, but you don't do that. You see, the true value of that 9/16 is 2 times 9 over 16, or 18 over 16, or 9 over 8. So you haven't added 9/16, you've actually added 9/8. So I will subtract 9/8. So I have y is equal to 2 times x minus 3/4 squared. And then this minus 1 up here is a minus 8/8, so it would be minus 17/8. So the vertex becomes 3/4 negative 17/8. Or like 0.75 and what, negative 2.125 if you were to create decimals. So 0.75 and negative 2.125. So that's your vertex, your axis of symmetry. If you were to write your axis of symmetry would be x equals 0.75. Your y-intercept, it looks like, is negative 1. If you were to put that there, reflect it on over. Direction is up. It has a minimum value of negative 17/8. So this process of completing the square is very important. And I want to be clear, on the test you are going to be asked to actually show the completing of the square. It's true that you could take this problem and do negative b divided by 2a to determine the vertex. But there's too many situations that are going to come up where completing the square is essential to working with other shapes. Because we won't always work just with parabolas. We will work with circles. If you remember, there's a completing of a square there. We'll also work with ellipses, and we'll actually work with what we call hyperbolas as well. And those are going to require completing of the square. So we'll check that in class and make sure you know what you're doing. So part of what I've realized is that you can shut the video off now if you want, but maybe you want to watch for just a little bit. And part of what I remember about math is just, to me, math was just always awesome. And part of what makes math awesome is this idea of conjecture and proof. Okay, so I'm just going to show you a couple ideas and help you understand what this is. And nothing is super complicated. I know that word proof scares you, but let me just help you understand. Conjecture, this is a gold box conjecture. And Goldbach basically says this. He's a guy who came up with this idea, and he seems to be right. He says pick any even number, say 12. You can write it as the sum of two numbers that are prime, 5 plus 7. Hey, it works. 14, that's 7 plus 7. Hey, works. 16, we'll go 9 plus 7. No, 9's not prime. So we'll try like 11 plus 5. Yep, that works. 18, 9 and 9? No. 11 and 7? How about 20? 9 and 11? No. 13 and 7. It turns out that you can pick any two-digit number, say 44. Not just any two-digit number, any even number. I just picked two digits because, it's easier for us to work with. You can find two numbers that add to that are prime. And this one, you try 21 and 23. That doesn't work because 21 is not prime. But 25 and 19, well, that doesn't work because 25 isn't prime. 27 and 17, well, 27 isn't prime. How about 29 plus 15? Well, 15 is not prime. How about 31 and 13? Yep, there we go. You see, it seems to work all the time. Conjecture is when we see that it seems to work all the time. Proof is where we verify that it for sure does work all the time. If you could prove Goldbach's conjecture, if you could prove that it works all the time, you would win millions of dollars on the Nobel Prize. It's one of the math problems that we haven't been able to solve for many, many years. We just don't know why it seems to work out. In fact, there's a supercomputer right now computing some super large number, some super large number that ends in, say, 8. It's an even number, and it's trying to find two prime numbers that add up to it. Seeing if it ever fails. So what about this idea of proof? There are these things that we have always said are true, and I wonder, do you know that they're true? Like, for example, do you know that a squared plus b squared is c squared? Do you know and trust that that is true? Is that conjecture or is it proof? That's a big question. You've always accepted it. But do you know that it for sure works out every single time? I know my drawing isn't really good right now, but we're going to say I drew a square within a square. We're going to call this side A and this side B. That would be A, this would be B, that would be A, this would be B, and that would be A, and this would be B. And we're going to call this length C. Since it's a square in a square, all those sides are C. Well, area of the small square equals area of the big square minus 4 triangles. I think we would all agree that, like, this area of this inside guy right here is the same thing as the area of the whole square, the big one, and then we're going to subtract off these 4 guys. Well, what is the area of the smallest square? The area of the small square is c squared. What's the area of the big square? Well, each side is a plus b. If we take a plus b times a plus b, we get a plus b squared. Minus 4 times the area of each triangle. I know that area of a triangle is 1/2 times each base times each height. C squared is a squared plus 2ab plus b squared minus 2ab. C squared is a squared plus b squared. You see, you just proved that that was true. And I know that you're used to doing proofs that are, geometry related. You say, well, this is geometry related. Yeah, but it feels different, doesn't it? Because it's got a lot of algebraic structure to it. And that's one thing that makes math awesome. Is so many times in the world we're just left to conjecture. We say, well, we think it's true. It always seems to be true. But in math, just about everything we can prove. There are very, very few things. I gave you Goldbach's conjecture. There are a couple more. But the proof, it's something that it's logical. It makes sense. You can never dispute it. And it provides a certainty to mathematics that no other subject truly can attain. That's one reason why math is awesome. Hope you enjoyed it. Good luck with your work. We'll see you soon.